Well, there we go. I've got too many documents on my desktop, as you guys can see. Looking for the 10C workbook. Okay. Okay, so question 13 here. I'm just going to take a picture of it. Pop it into a Word document here. My pen doesn't write very well on PDF, so that's why I like to use Word documents. The pen works a lot nicer and smoother on there. So I'm just going to transfer it over here. Okay, so this is question 13 here. So it says, how many of the numbers in the list 2, 3, 9, 13 are not prime factors of 2,592. So what we need to do is we need to prime factor that number, and you can use whichever process we talked about yesterday, or if you have a different way of doing it from a previous course or somebody else that you might have learned from. But you either want to use the tree diagram that we did yesterday or the division table. So it's up to you. So I'm going to use, I'll use the tree diagram. Because as you guys know, I talked about yesterday, that's my favorite. But really it doesn't matter which one you want to use. So I'm just going to go with, this is an even number, so I'm going to start with 2. And if I divide 2 out of 2592, we get 1296. 2 is prime, so I'm going to stop there. 1296 is even again, so I'm going to go with 2. And that will give me 648. So that 2 is prime. 648 is even, so let's do 2 again. 324, prime. 324 is even, so let's go with 2. We'll do 2 again, because 162 is even. Okay, and finally we have a number that's not even, so I can't use 2 for 81. I'm going to break it down into 9 and 9. Okay, and 9, both 9 and 9 are not prime, so we have to go one step further, and we break up both of them into 3 and 3. And now we've got prime numbers there. Okay, so it says how many numbers, so it looks like our only prime factors are 2 and 3. Right, I've got a bunch of 2s and I've got a bunch of 3s, so that's the prime factors. Okay, so the question says how many of the numbers in this list, 2, 3, 9, and 13, are not prime factors? So 9 is not a prime factor, and 13 is not a prime factor. We only had 2 and 3, so those two both are prime. So you would say 2 of those numbers from that list are not prime factors. Okay, does that make sense, Stephen? Perfect, yeah. Okay, yeah, and we will look, oh, that was 13, yeah, we got 13. And then 16. Okay, we'll look at question 16 as well. I don't think anyone else had any other questions, so we'll just do 16. and then we will move on. So question 16. Okay, yeah, this is a good one. So these numerical response questions, you guys might be noticing just from even this first lesson here, can be written in a really confusing way. And I was just talking with my 20-2s in our class earlier and talking about how numerical response questions, unfortunately, show up on your diploma exams. So, and diploma exams are made by Alberta Education. So as instructors, when we're teaching, we need to model our own exams out after those as well. So even though most of us aren't a big fan of these types of questions, we definitely want to show you guys how to do these, because you will see them if you're planning on moving into 30-2 and taking the diploma exam, or if you're planning on doing the equivalency with us. The equivalency is modeled just after the diploma exam. So you'll see questions like this for sure. And we might have a few pop up in this class or this course as well in your assessments, just to get you used to using those. Okay, so the reason why they're tricky is they'll do things like this with variables, which right away some students just shut right down, being like, I have no idea what this means. I'm not going to be able to get this right. But the key with these is just to read very carefully, pull out all the key words, and try to think of it logically rather than just getting confused with these variables, because all these variables are representing as a number. So P stands for a number, Q is a number, and R is also a number. So our goal is going to be to figure out what is P, what is Q, and what is R. So it says the number 686 can be expressed as a product of prime factors in this form. The value of P plus Q plus R is. So basically our goal right now, just ignore this last part. We'll come back to this at the end. That's just the way we're going to have to present our answer in the numerical response box down here. So we know how to do this. We definitely know how to express a number as a product of its prime factor. So I'm just going to focus on the number 686. Okay, and then prime factor it however you like, again using the division table, or you can use the factor tree. Okay, so I'm just going to go with 2 because it's even. So 2 and 343. And then 343 is not even, so I can't take out a 2. We could try a 3, but the rule for 3 is we need to add all the digits together. 3 plus 4 plus 3 would give us 10, which is not divisible by 3, which means this number won't be divisible by 3. Or if you don't want to use the rule, you can just type in 343 divided by 3, but you'll get a decimal. So what ends up working is the number 7. Okay, and then 2's prime, 7's prime. 49 I can take down to 7 times 7. So from what we were doing yesterday, we usually write the smallest number first, so it'll be 2 times 3 7s. Or if we want to write it as exponents, because that's what it's showing us here, that little r, it would be 2 times 7 to the 3. Okay, so that's the math part you have to do with the question. Now it's just interpreting what the question's asking us to do. So it says our solution should look like this. So I'm just going to write my answer right underneath here. I've got 2 times 7 to the 3. So what that means is the P value should be the 2, the Q value is the 7, and the R value is the 3. And then it's saying, okay, we want your answer to be whatever P is, add it to Q and add it to R. So we're just going to take those 3 numbers and literally add them together. So 2 and 7 is 9, plus 3 would give us 12. And then that's what goes in the numerical response box. And with math, always, you fill in the boxes left to right. So it's always the first number in the first box, second number in the second box, and then that's it. So you leave those other 2 boxes that we aren't using, you leave them blank. It's very, very important that you leave them blank. We've had students in the past do things like this, put in zeros in the last two just because they aren't being used, and they assume that you need to have something in those boxes. That's why they're there. But what that means is you're telling me the answer is 1200. So always leave the boxes to the right that you aren't using, leave them blank.
I have a question.
Yes, go ahead.
When I divided 243 to 3, I got 81. Do we have to start from the bigger prime numbers?
When you did this one here?
Oh, that's 300. Sorry.
Yeah, that's why. That's why. You would be
Okay.
right. If it was 243, you would be right.
Oh, okay.
Yeah.
Right. Thank you.
You're welcome. Okay, any other questions? Yeah, no problem, Stephen. You know what, that's what usually happens with those numerical response. So it's good that you're asking that, and we can go over some of those together because they can be confusing the way they're written. So definitely try those in your assignments. Don't shy away from them because the assignments aren't being marked by me, right? So technically, if you didn't do them, I wouldn't know, but then you aren't prepping yourself as good as you can be for a quiz or for a test. So always try those. If you're stuck on it, for sure, ask me and we can work through it together. This is going to help everybody because they can see, okay, that's how you kind of try to pull apart those questions and deal with them. All righty, very good. Okay, so yesterday, let me just close this. We were talking about factors, prime factors, all that good stuff, and we were breaking down numbers and having to find factors of numbers. And one of the challenges with that, right, is having to check a whole bunch of numbers to make sure you have the full list of factors. So I was talking about those divisibility rules. So I hope some of you or most of you saw this, but I posted this yesterday right after class. I just literally went into Google and typed in divisibility rules, and I looked for a PDF file, so you can always do that too. So it's right here for you if you're interested in those. Okay, this will just help you to find numbers that you can divide out of bigger numbers. I find the rules 2, 3, 4, 5, 7 useful, and then everything kind of after that becomes really complex, where it's just easier to type in the number and go divided by 11 to see if it works, rather than having to try to go through this process. It's going to take you longer to do that than to actually just try it in your calculator. So if you're interested, take a read through of those. It could definitely help you find factors, but like I said, the smaller ones are usually the more helpful ones. So this is the 3 that I keep talking about. So a number is divisible by 3 if and only if the sum of the digits is divisible by 3. So that's why you're hearing me when I have a big number like 954, I'm adding those numbers together. So you add each digit together, and if the number itself, 18, when you add them together, is divisible by 3, which it is, that means this entire number will be divisible by 3. Okay, there's the one with, for 5, any number that ends in a 0 or 5 is always divisible by 5. 10's another easy one to know. Any number that ends in a 0 will always be divisible by 10. 4 is kind of a weird one. I don't tend to remember this one ever because there's a lot going on, but a number is divisible by 4 if the last 2 digits taken as a number itself is divisible by 4. So that means whatever the number is, just look at the last 2 digits, 32. If I can divide that by 4, which we can, then that means this whole number will be divisible by 4. So at some point in your schooling, you may have or may not remember learning these. I remember way back at elementary school at some point learning them, but only remembering certain ones that are the most common. So those are there for you if you want to use them. So feel free to print that off. You can save it as a document to your computer as well. Okay, so we completed lesson 1 yesterday, so I put a big cross through that. We're done that one. So we're kind of continuing on with the stuff we learned yesterday. Now we're going to apply it to different concepts today. So we're moving in with applications of prime factors. So our big topic for the day is two things. Basically, the greatest common factor, which you will lots of times hear me call it the GCF, or you'll see it written down as the GCF. And that just saves us from having to say every time the greatest common factor. Just shortens it up for you. Okay, and then also we're going to look at the lowest common multiple for the LCM. So we're going to do this with big numbers today mostly, and we're going to use the concept of prime factorization that we learned yesterday. So I'm going to show you how to use that process to find the greatest common factor and also to find lowest common multiple of any set of numbers. Okay, so for the most part today, just because I wanted numbers that would work out nicely, and just for the sake of time, I used most of the questions from your workbook lessons. So if you're wondering if you want to use your workbook today, you will be able to, because most of the stuff is from there. So this is on page 7. That's where lesson 2 starts. And starts off with just giving you a practice question on products of prime factors, which was good from Stephen having those questions. We just did some review of that. So let's jump right into what the greatest common factor is. So at some point, whether you remember or not as well, you would have done this in your schooling, but now it's going to get more complex. So greatest common factor is basically, it's just the largest number or the largest whole number which divides exactly into each of the numbers of a given set. Okay, so for example, again with math, the terminology, definition sometimes can be very confusing, so it helps to show an example with actual numbers, and then you're like, oh, well, that's easy. It just sounds confusing. So the greatest common factor of 6, 16, and 20 is. So basically, we want to know what all the factors of 6, 16, and 20 are, and we want to compare those lists and find the biggest number that's common to all three lists. So if we find our factors of 6, so just like we were doing yesterday, factors of 6 would be 1, 2, 3, and 6. Factors of 16 would be 1, 2, 4, 8, and 16. I don't think I missed anything there. And then 20 would be 1, 2, 4, 5, 10, and 20. Okay, so once you have all your factors listed, we're going to go through each list and just see what's the biggest one that exists in all three. So there's no 3 and 6 here, so the biggest one in all three lists would be 2. Okay, so what that means is the greatest common factor of these three numbers is 2. So it's just the biggest number that divides out of all three of those numbers. Sorry about those notifications. Looks like there's a meeting going on. Everyone's excited. Okay, so when we're dealing with small numbers like these ones here, it's pretty easy to do it this way. Just do the list really quickly and then look through your list and find what number exists in all three. When the numbers get really big, like these guys down here, we're going to want to use a different method, and that's where prime factorization comes in. Okay, so we're going to still just work with a couple of smaller numbers here and just do the list here. And that's what I usually tend to go to if the numbers are small. Sometimes you can even just look at the numbers and mentally figure out in your head, okay, it looks like it's going to probably be 5 for these numbers, but let's just double check. So if we write all the factors out for 15, we have 1, 3, 5, 15. I'm going to go a little bit quicker with these today just because we talked about them in depth yesterday how to find them. So if you're still a little bit slower, that's okay. You can review it on your own time a little bit later. 25 would be 1, 5, and 25. And then 35 would be 1, 5, 7, and 35. Okay, so if I look at all three lists, my initial inclination of 5 is correct. So that's the biggest number that exists in all three. So we would say the GCF here is equal to 5. Okay, so 18 and 20, do the same thing here. We've got 1, 2, 3, 6, 9, and 18. And then for 20, we would have same thing that we did up here. So sometimes you'll have repetitive questions, which is nice because you can go to the previous one and just copy down what we had. Okay, so 18 and 20, you think they'd have a bigger number in common than 2, but it looks like that's it. So 2 is the largest number that can be divided out of both. Okay, and then lastly we've got 36, which would be 1, 2, 3, 4, 6, 9, 12, 18, and 36. So 36 has quite a few factors. '54 will have 1, 2, 3, 6, 9, 18, 27, and 54. So 54 might take you a little bit more time, which is fine, but you can do the listing of pairs like we did yesterday. Okay, so for this one, the largest number in both would be 18. So the greatest common factor would be 18. So just making lists like this is always an option. It doesn't matter what the number is. It could be a huge number. As long as you can find all the factors, this is a perfectly fine way to do it. The only issue with that is, right, once the numbers get bigger, it's hard to find all the factors. So we've got a foolproof way to do it, and that's using prime factorization. And that just guarantees that we wouldn't miss any factors by just trying to do it on our own. Okay. Questions on that at all? Just making your list of factors and then just comparing and finding the biggest one. Oops, right. Okay, sounds good. All right, so let's try some bigger numbers. So this is where it's saying right here, use prime factorization to determine if the GCF of the given whole numbers. So we want to find the greatest common factor of 90 and 25. So again, that just means find the biggest number that exists in the factor lists of both 90 and 225. So if you would like to, and I'll just show you why this can become really challenging. If I had to make my list for 90, I would do 1, 2, 3, 5. So it becomes a lot of calculator work. 6. So I'm actually trying in here 90 divided by 7, because with big numbers, even me, someone who has to work with numbers every day, I'd have to sit and use my calculator to make sure I didn't miss any numbers in between. So that becomes very tedious very quickly. So what we're going to do instead is I'm going to do prime factorization. So you can use, again, either the division table or you can use the prime factor tree. So if I use the prime factor tree, I'm just going to start with 9 and 10 because I know those multiply to 90. 9 breaks down to 3 and 3, and 10 would be 2 and 5. Okay, all of those are prime, so I'm just going to circle them. And if we did 225, because it ends in a 5, I know for sure I can take a 5 out. And that would be 5 and 45 together. 5 is prime. 45 I can break down, again, 5 because it ends in a 5. And the other number would be 9, so 9 times 5 gives me 45. 5 is prime. With 9 we can break down into 3 and 3. Okay, so what I'm going to do here is I'm going to below just write out our prime factorization of each number. So 90 is 1, 2, 2 3s, and a 5. 225 is 2 3s and 2 5s. Okay, and for GCF, it's quite simple. Literally all we are doing is we're taking out everything that's common to both of these prime factorization products. So they both have 1 3. They both actually have 2 3s. And they both have 1 5. Okay, this 2 in the 90 doesn't exist in 225, so I can't use the 2. It's not common. And the second 5 doesn't exist in 90, so I can't use that one because it's not common. So it's literally just these three numbers, 2 3s and 1 5. And what we do is we multiply them together. So 2 3s and 1 5. So our greatest common factor would be 45. Okay, this process also works for the small numbers too. So if you don't want to make lists ever, you don't need to. You can do prime factorization all the time. Okay, so if I go back up to 18 and 20, we can do the exact same thing. So I'll just quickly, just to show you, I'll do this really fast. So 18 I'll do 3, 6, and then 3 and 2. 20 would be 4 and 5, and then 2 and 2. Those are all prime. So 18 would be 2 times 3 times 3. 20 would be 2 times 2 times 5. The only thing common in both lists is 1, 2. Right, a second 2 doesn't exist up here, and there's no 3s down here, and definitely no 5s up there. So all you would have there is just a 2. Okay, so that might even be quicker than doing the list if you have to sit there with your calculator. This takes away that having to do that. Okay, any questions on that so far? Three, 3, and 5. Let's go back here. Okay, Jonathan. So once you have your product, your prime factorization written out for both, if you're looking for the greatest common factor, you're looking for all the prime factors here in this case that exist in both lists. So if I look at this first 2 in 90, there would have to be a 2 in the next list as well, which there isn't. So that means that 2 is not part of my common factors. If I look at this 3, there is a matching 3 down here. So both lists have 1 3 for sure. So I circle those because that's going to be used. Both lists also have another 3. So I'm just going to circle both of those. And then both lists have 1 5. This second 5 in the 225 list doesn't exist in the 90 list, so we can't use it. So you only write down what's common. You don't write down 3, 3, 3, 3, 5, 5. You only write down, okay, they both have 1, 3, so 1, 3 goes here. They both have a second 3, so a second 3 goes there. They both have 1, 5, so 1, 5 goes there. And then you just multiply those numbers together. Sorry, everybody. I just got kicked right out of that meeting somehow. Take my camera off. Sorry about that. Yes, exactly. If there was 2 5s in each, you'd have 2 5s written down and the 2 3s. Yes. Okay, I don't think the recording got mixed up. It looks like we're still recording, so that's good. Okay, questions on that? Andrew, no, you won't actually miss numbers in there. If you do prime factoring every single time to find GCS, what you'll miss is factors that aren't prime. But that's not what we're looking for here. We're looking for the greatest common factor. So when we multiply all those together, that would give us a factor value that would be in the list, and that's the one we're looking for. You're right that you would miss all the factors that actually exist for 90 and all the factors that actually exist for 225, but we don't need those in this case. We just want the biggest one that would be common. And by finding the prime ones and multiplying the common prime numbers together, that will give us what we're looking for. Okay, good questions, guys. Okay, let's keep on going. Sorry about that. You're going to hear my dogs every now and then. I just need to reshare my screen here. Okay, just let me know if something is not working here for you. Okay, so let's look at the number 154 and 198. So same thing. You can do this using your division table, or you can do this prime factor tree. So let's try a division table with these ones just to switch it up. So for those of you that like to use that. So 154 and then 198 I'll set up over here. Okay, so the only difference with the division table is when you're looking for numbers to divide out of that original number, it has to be a prime number. So whenever it's even, my default is always to go to 2. So when I do 154 divided by 2, 77. And then definitely 77 would be divisible by 7, which is prime. And when you divide that, we get 11. Now 198, also even, so I'm going to default and use 2 here. So 198 divided by 2 gives me 99. Okay. And I would love to use 9 here, just like I used 7 for 77, but 9 isn't prime, so we can't use 9. What we can use is a 3. And that will give me 33. And then again, 33, we can take another 3. And 33 divided by 3 would be 11. So if I write out both my lists here, 154 would be 2 times 7 times 11. And 198 would be 2 times 3 times 3 times 11. So we're going to circle just the common pieces here. So it might help if I don't circle them individually and just do this. So they both have a 2. 154 has a 7, but if I look at 198, there's no 7s. 198 has 2 3s. If I look at 154, there's no 3s. So neither of those can be used, but they both have an 11. So the two common numbers are 1, 2, and 111. So your greatest common factor would be 2 times 11, which would give us 22. Melanie, it's your choice. I usually, if I'm doing these questions, I always just use the prime factor tree method. That's just kind of my go-to. That's the way I learned it when I was in school, so that's what I've stuck with. But you don't need to know both. You choose whichever one you want and you stick with that one. If you want to switch back and forth and use both, that's okay too. You're welcome. Okay, 3 numbers now at a time. So we're going to have to do 3 different division tables or 3 different factor trees. Yeah, that's as I'm using a division table too, Jonathan, because again, I don't use it unless if I'm teaching, and I haven't taught 10C in a while. So I'm actually thinking, oh, the division table is actually not that bad. The only thing is that you have to make sure you're using prime numbers, but that's not a big deal. Because you can usually always use 2, 3, 5, or 7, and that will work for most of them. Okay, so let's use the division table here again then. So we'll do 1 for 245, 1 for 315, and 1 for 770. Okay, so 245 we'll start with here. Ends in a 5, so I'm definitely going to be able to divide a 5 out of that, which will give me 49. And then 49 we can divide 7 out, which will leave us with 7. 315 also ends in a 5, so I'm going to use 5. So 315 divided by 5 leaves us with 63. Now with 63 you can use 3, or you can use 7. 7 will come out of there as well, which leaves you with 9. And 9 I can only divide 3 from, and that will leave me with 3. Okay, and then 770 ends in a 0. So again, anything that ends in a 5 or 0, you can always divide 5 out of. So we're going to go with 5, which leaves me with 154. Okay, now you can play around with this if you want to try bigger numbers with 154, but it's even, so I'm just going to default to use 2. Which leaves me with 77 when I divide out 2. And then the only prime number I can divide out of 77 would be a 7, or I guess, or an 11, but either way, you're going to get a 7 and 11 in there. Okay, so I'm just going to write my list here. So I've got 245 is equal to 5 times 7 times 7. 315 is 3 times 3 times 5 times 7. And 770 would be 2 times 5 times 7 times 11. Okay, now what is common here is they each have 1 5. A 3 doesn't exist in all three, neither does a 2, so I can't use any of the 3s or 2s. They all have 1 7. Okay, and then that extra 7 in the first list, there isn't a second 7 in the other two, and the 11 only exists in one, so that's it. So our GCF is just a 1 5 and 1 7. Oops, that should be an equal sign. So your GCF here would be 35. Okay. Any questions on that one? We doing okay so far? Okay, excellent. Now, really big here. Let's give this guy a go here. So let's do the division tables here again. A lot of times the division tables look, they look neater, more organized, right? Whereas the prime factor tree can get a little bit sloppy and you can lose some numbers in there if you're not making sure you're circling all your primes and that kind of thing. So 171 is an interesting one. It ends in a 1, so that doesn't really tell us anything. Well, it does tell me I can't use 2 because it's an odd number. If I can use 3, if you add your digits together, so 1 plus 7 plus 1 would give me 9, which is divisible by 3. So I should be able to divide 3 out of 171. And that'll leave me with 57. Okay, something ending in a 7. Again, it's odd. Can't use a 2. Possibly a 3. 5 plus 7 is 12, which is divisible by 3, so 3 should work. And we get 19. And 19 is a prime number, so we can stop there. Okay, 285 ends in a 5, so we can definitely divide out 5, which leaves me with 57 again. And we just dealt with 57 over here, so I know I can take out a 3, and it's going to give me a 19. And then that one's done. 399, all 3 digits are divisible by 3, and if I add them together, 18 plus 3 is 21 is also divisible by 3. So 3 will work here. And I'll give me 133. Okay, 2 won't work because that's odd. 3 I don't think works either because if I add the digits, 1 plus 3 plus 3, it gives me 7, which isn't divisible by 3. But let's try 7 there. So 7 works. And that'll leave me with another 19, which is prime. And then 1140, it's even, so you can either use a 2 or it ends in a 0. You can use a 5 as well. So we get 228. So that's even, so I'm going to go with a 2. So we divide that by 2, we get 114, which is also even, so we can use 2 again. Another 57. And we already know from the last 2 times that 57 we can divide out 3 and be left with 19. So even though these numbers are really big, these division tables ended up not being too strenuous, right? The longest one was this one here, and it was only 4 steps. So not too bad. So if we make our prime factorization lists, we've got 171 is equal to 3 times 3 times 19. 285 is 3 times 5 times 19. 399 is 3 times 7 times 19. And 1140 is 2 times 2 times 3 times 5 times 19. Okay, so common to all 4 of those lists now. So the very first number, 171, is a 3, which exists here, here, and here. So there's 1 3 in all 4 lists. 171 has a second 3, but none of the other lists do, so they can't use that. 5 and 7 and 2 only exists in the list they're in right there, so those aren't useful. There's a 5 down here, but it has to exist in all 4 lists to use that. The only other number that's in all 4 is a 19. So our GCF here with these 4 numbers is just 3 times 19, which will give us 57. So that 57 kept popping up a lot there. Okay, so that's how you use prime factorization, where you can find the GCF of any numbers. It doesn't matter how big they are. We could give you numbers in the hundred thousands, even millions if we wanted to, and we won't. We won't go that big, but using the division table or using the factor tree makes it nice and simple. Okay, everybody okay with greatest common factor? Or I should say, any questions about greatest common factor? Perfect, okay. Let's move on to lowest common multiple. So what's nice about greatest common factor and lowest common multiple is we can use prime factorization to find both. It's just once we have our prime factorization lists, it's a different method to find the GCF versus the LCM. So that's it. But we do the division table, we do the factor tree the exact same to start with, and then there'll be a slight difference when we're actually finding what the LCM is at the end. So remember the difference between a factor and a multiple. A factor of a number is always a number smaller or equal to that number. So if I go back up here for a second, till we actually listed off all the factors. So all the factors of 18 and 20, if you look at the lists, all the numbers are smaller and then equal to our given number. Multiples, on the other hand, are the exact opposite. So factors are all numbers that can divide out of a number. Multiples are all numbers a number can multiply into. And it's hard to find a really simple definition of that. So I'm just going to write down a number here and I'll show you what I mean by multiples. So just a multiple in general. Multiple. So let's use the number 3. So the multiples of 3 are, we just take 3 and multiply it by 1. So the first multiple of 3 is 3 itself, always. So any number, if I had the number 20 here, the first multiple of 20 would be 20, because I get that answer by doing 20 times 1. To get the next multiple, you multiply it by 2. So 3 times 2 is 6. 3 times 3 is 9. 3 times 4 is 12. 3 times 5 is 15. 3 times 6 is 18. 3 times 7 is 21. And so on. So the difference between factors and multiples is that factors is a finite amount for every number, which means you have a specific amount of factors, and that's it. So if I go back up to 18, these are all the factors of 18. There's 1, 2, 3, 4, 5, 6 factors. That's it. With multiples, because numbers don't end, I could go 3 times 8, 3 times 9, 3 times 10, 3 times a million, 3 times a billion, 3 times a trillion, right? All those numbers, and because there's no end to numbers, we use the word infinity as basically a representation of the end of a number, but it's not actually, infinity is not actually a number. It's a placeholder, we call it. It's just a term that we use to say this doesn't actually end. So multiples go on forever. So we never want to find the largest common multiple because we would never be able to find it. We'd be sitting there writing out multiples on paper forever. What we want to find is the lowest common multiple. So once we make our multiples list, we want to find the smallest number that's common to those lists. Okay, so we'll start off with the smaller ones and we'll just actually make multiples lists and see how we go from there. So it says find the lowest common multiple or the LCM of the following sets. So 5 and 7. So what I'm going to do is I'm going to make my multiples lists and I'm going to go up to a certain point and then stop and then see if I have anything that matches in both lists. So the first multiple of 5 would be 5 times 1, which is 5. 5 times 2 is 10. 5 times 3 is 15. 5 times 4 is 20. 5 times 5 is 25. 5 times 6 is 30. 5 times 7 is 35. Now, because I used a 7 in there to multiply, I know 35 is going to be in there, but I want to make my list first to see if there's anything before 35 that matches. So let's jump down to 7. 7 times 1 is 7. 7 times 2 is 14. 7 times 3 is 21. 7 times 4 is 28. 7 times 5 is 35. So if I look through my list, there's nothing before 35 that exists in both. So the smallest number in the multiples list of 5 and 7 that exists in both is 35. So you basically just have to keep going with your lists until you find a number that you know is going to exist in both. Okay, and in some cases, it does end up being the two numbers multiplied together, but not always. Okay. Now, these get really big really quickly. So what I'm going to do with these two is I'm going to avoid making these lists because they're actually really big. The LCM of 10, 15, and 20 is 60. So these lists probably wouldn't be too bad. But 10, 12, and 14, we'd have to take all three lists up to the number 420. So you can imagine with 10, we'd be going to make the 10 multiple list. 10 times 1 is 10, 10 times 2 is 20, 10 times 3 is 30, 40, 50, 60. So you're basically counting by tens. But we'd be going on forever because there'd be nothing common to it in the 12 list or 14 list until we reached 420. So these ones get really long because there's no end to a multiples list. So unless the numbers are really small, like 1-digit numbers here, I would avoid using the list method for sure. So let's just jump down to the prime factorization here. So any large numbers, and I would suggest any numbers larger than the 1-digit, like I was saying, use prime factorization. Okay, so we'll do these ones first, and I'll come back and maybe do the easier ones, or I'll just leave it for you to try. We'll do the tougher ones here together. So it says use prime factorization to determine the lowest common multiple of. Okay, so let's make I'll do factor trees this time because I haven't done it a little bit, but if you want to stick with the division table, go ahead. So let's find our prime factors. So 126 is even, so I can break that up with a 2 for sure. And when I divide a 2 out of there, I'm going to get 63. And then 63, you have a couple ways to go, but I'm going to go with 7 times 9. 2's prime, 7's prime, and 9 I can go into 3 times 3. 441, we can divide out a 3. It's because when I add these digits together, 4 plus 4 plus 1 gives me 9, which is divisible by 3. So when I divide 3 out of there, I'm going to get 147. 3 is prime. 147, if I add the digits, I get 12, so I can take a 3 out. It'll get me to 49. 3 is prime. And 49 breaks down to 7 times 7, which is both prime. Okay, so prime factorization is the exact same. Let's make our lists. So 126 is 2 times 3 times 3 times 7. And 441 is 3 times 3 times 7 times 7. So to find the LCM, here's where the difference comes in now. With GCF, right, we would just circle everything that's common and take out those common pieces and multiply them together. But with the LCM, what we actually do is you start with the prime factorization, the full prime factorization of one of the numbers. Doesn't matter which one. So I'll start with the first one just because it's on top. So it's going to include everything from the first number for sure. Okay. And then, so we've used those. And I'm going to cross off what's common that I used already from the second list. So I used a 2, but they didn't have that here. I used a 3, so that 3 is already taken. I used a second 3, so we used that 3. And I used a 7. So the only remaining piece left in that second list that we didn't use is a 7. We have to add that on the end. Okay, so you basically take one full prime factorization multiplication statement. So we took the first one. And then we add whatever was different, or whatever's extra from the second one gets added at the end. And then we multiply all of that together. So we get 2 times 3 times 3 times 7 times 7, which gives us 882. So that represents the smallest number that would exist in the multiples lists of both 126 and 441. Okay, so it might be a little confusing right now just because of the different, suddenly I'm throwing these different rules at you. Let's do this next one here first and then see if there's any questions after that. So let's do 22, let's do prime factoring of that. Let's do the division table here. Okay, so 22 is even, so I'm going to use 2. I'm going to divide out 2, I'm left with 11. 154 is even, so let's use 2 as well. Get 77. And then you can either use 2 prime numbers that come out of 77. You can either use 7 or you can use 11 and you'll have those 2 numbers there. So you have 2, 7, and 11. 198 is even as well, so let's use a 2. When we divide out 2, we get 99. And then from 99, we have to take out, remember these have to be prime numbers that we're choosing when we use the division table. So I can't use a 9, it's not prime, but I can use 3. So 99 divided by 3 will give me 33. And then you can either divide out an 11, you can divide out another 3. Okay, so a little bit neater, doesn't take up as much room as a factor tree does. So if I write out my lists now, so I've got 22, is equal to 2 times 11. 154 is equal to 2 times 7 times 11. And 198 is equal to 2 times 3 times 3 times 11. Okay, so for the LCM, you start with any factor list that you want. So I'll start with the first one, just again because it's on the top, but you can start with the 154 list or the 198. So 2 times 11, and I'm just going to cross it off of each list. So I used 1, 2, I used an 11, and now from the second list I didn't use that 7, so I've got to add that 7 in. Doesn't exist here, so I don't have to cross it off. And there's 2 extra 3s that I have to add on. So you basically have to make sure you're using every single number in here. You just can't duplicate one of the numbers. So we get 2 times 11 times 7 times 3 times 3. So that's a big one. So we get a lowest common multiple of 1,386. Okay, any questions on the LCM? So I think for you guys, if because this is going to be mostly brand new, I think for probably a good chunk of you, practice, right? So just make sure you have those 2 processes down really well and do as much practice as you can out of that workbook assignment. Once you've done practice, it becomes kind of like second nature to you. It becomes a lot easier. So you might be a little bit slow in the beginning, which is completely fine. But just make sure you do some practice with it, take some notes, make sure you write down the rules for each, so you have that in front of you, and then you know which way to go with it. Okay, perfect. So last thing here, and I probably won't get through all this, we've only got 15 minutes left, which is fine. I don't need to cover all of it, I just want to touch on it for you. And then I can leave the rest for you to do, or we can talk about it briefly tomorrow too, if you didn't get a good enough explanation. But using prime factorization to figure out whether a number is a perfect square or a perfect cube. So if a number is a perfect square, and all that means is a number is a perfect square if you can take the square root of it and get a whole number as an answer. So if I look down here at 16, 25, and 81, we know, because we work with these numbers quite a bit, we know 16 is a perfect square because I can square root it and get 4. 25 is a perfect square because I can square root and get 20 and get 5. And 81 is a perfect square because when I square root it, I get 9. So we already know those are perfect squares. But if you have bigger numbers like these guys down here, and you're asked, is this a perfect square or not? And you can't use your calculator, you have to prove it in a different way. What you can do is use prime factorization again. So in order for a number to be a perfect square with prime factorization, all of the prime numbers must exist in perfect pairs once I prime factor it. And again, it doesn't really make sense until you see it in action. So let me show you here with 16. So if we prime factor 16, I'm just going to use the factor tree here. I can break 16 into 4 times 4, and then both 4s can break into 2 times 2. So what that means is I've got 16 is equal to 2 times 2 times 2 times 2. Now I've got 2 perfect pairs of 2's here. So I've got 1 pair of 2's and a second pair of 2's. If that happens and there's nothing left over, that means you'll be able to take the square root of this number and get a whole number in return. And what the whole number would be, for each pair, it represents one of those numbers. So all that means is the square root of 16 would be equal to 4. Okay, If we look at 25, I can break that down into 5 times 5, which is a perfect pair. So one perfect pair, which means the square root of 25 would be equal to 1/5. 81, break it down to 9 times 9, and then each 9 can be broken down to 3 times 3, which would give us 2 perfect pairs. So if I was to take the square root of 81, it would be equal to 1/3 times another 3, which would be 9. So I'll do one of these bigger numbers here, and then we'll jump down to the cube root as well, and I'll leave the rest for you to do. Just as long as you see the process, you should be okay with it. So it says in each case, this is class example number 7. And for those of you following along, this is in your workbook. This is page 10. Okay, so it says in each case, use prime factorization to determine if the number is a perfect square. If the number is a perfect square, state the square root of the number. So again, we're not going to use the calculator. We're not going to plug in square root of 1225 because that'll just give us the answer. We want to actually go through the process of it. So if let's use a factor or a division table so we can see it the different method. So let's do 1225 prime factorized. It ends in a 5, so we can take out a 5. Oops. So 245 ends in a 5 again, so we can take out another 5, which gives us 49. And the prime number we can divide out of 49 would be 7, and leaves us with 7. So 1225 is equal to 5 times 5 times 7 times 7. So I've got a perfect pair of 5s, perfect pair of 7s, nothing left over. That automatically tells me, yes, this is a perfect square. And the square root of the number, without using the calculator, would be one group of 5s times one group of 7s. So square root would be 35. Okay, stop there and just see if there's any questions on that. I think it's fairly simple, and we're getting a lot of extra practice with prime factorization today too. So if you were having a few issues yesterday, hopefully a little bit of extra will help you today. Yes, so it's only a perfect square, Jonathan, if you have exact pairs of numbers with nothing else left over. I'll actually do the next one here to show you, because 3042 is not a perfect square. So let's do this one really quick here. So 3042. So it's evens. Let's take out a 2. Using a 1521. It's not even, so I can't divide that by 2. But if I add the digits together, 5 and 1 is 6, 8, 9. It should be divisible by 3. So these are 507. Again, add the digits together, we get 12, which should be divisible by 3 again. 169. And that will be able to take out a 3, I think, again. Oh, nope, we can't. See, I didn't check. I didn't add the numbers together. Can't use 2 because that doesn't work. 4 won't work. 5 won't work. 61, that's actually 13, I believe. So you have to keep trying for a bit. 13 will work. It appears as though this meeting is now ending. Okay, so if we wrote out our prime factorization statement, we'd have 3042 is equal to 2 times 3 times 3 times 13 times 13. So what we would have is we've got a perfect pair of 3s, perfect pair of 13s, but this 2 doesn't have a pair. So all we have to say with that, okay, because I don't have perfect pairs, this is not, not a perfect square. So each number has to pair off perfectly with nothing else left over. Okay, and then the same case is true with perfect cubes. But you can imagine now with perfect cubes, you would have to have groups of 3 numbers, right? Because the index is a 3. With a perfect square, the index is a 2, so you have to have perfect pairs. So we can do the exact same thing and to check if any big number, or any number really, is a perfect cube. So let's do 6,912. So now this is on page 11, class example number 8. So if we do the division table here, and sometimes questions will tell you specifically what to use. So you might see that in your workbook assignments, but when you're doing assessments for me, I won't dictate to you which method to use. You can use whichever one you want. So 6,912 divided by 2 would leave me with 3,456. It's even, so let's divide by 2 again. Leave me with 1,728. Divide by 2 again. 864. Oops, 64. Divide another 2. 432. Divide another 2. 216. Divide another 2. 108. This is going to be a long one. Divide another 2. These are all even, so it makes it easy. 54. Divide another 2. 27. Finally, we don't have an even number, but 27 we can divide 3 out. That will leave us with 9. And then we can divide 3 out of 9, and that leaves us with another 3. So when you have big division tables or factor trees like this, make sure you double check and count everything so you're not missing anything in here. We've got 1, 2, 3, 4, 5, 6, 7, 8 2s and 3 3s it looks like. 2 times 2. 7, 1 more 2, and then 3 3s. Okay, so you just have to remember we're talking about a perfect cube, so don't forget that you're looking for groups of 3, not pairs. That's only if it's a perfect square. So perfect cube, I've got 1 group of 3 2s, 2 group of 3 2s, and then only 2 2s, so I can't make another group, and I have a group of 3s. So these 2 2s, because there's not a third 2 with that, automatically I can say, therefore, this number, 6,912, is not a perfect cube. Because all the numbers don't nicely work out into groups of 3s. Okay, we'll do this last one really quickly here. We've got about 4 minutes or so left. This one I think does work out to be a perfect cube, but let's try it. So let's use the division table here. So this number is not even, so I can't use 2. 3 will work though. So if I do 970,299 divided by 3, we end up with 323,433, which is divisible by 3 again. So divide out another 3. 107,811. Still not even, but again, 3 will work. If you add all the digits together, you'll get something that's divisible by 3. So divide out another 3. Finally, we're out of the 100,000, so 35,937. Let's try 3 again. That works. 11,979. Okay, let's try 3 again. That works again. So 3,993. 3 will work again here. And we'll be left with 1331. Now, if we try 3, I don't think it works. Yeah, so when I add these digits, 1 plus 3 plus 3 plus 1, it gives me 8. So I can't do 8 divided by 3, which is why 3 doesn't work here. So you want to try your other prime numbers. So 7 won't work. I think 11 works. So 1331 divided by 11. 121. And 11 is definitely divisible by, 121 is definitely divisible by 11 again, because that's a perfect square. And it gives me 11. So when I write this one out, we're going to have, how many 3s do I have here? 1, 2, 3, 4, 5, 6 3s and 3 11s. Yeah, just want to make sure I didn't have too many 3s there. Okay, so let's see if we can group all of these in 3s. So I got 1 group of 3 3s, 2 groups of 3 3s, and 1 group of 3 11s. So that works out perfectly, which means 970,299 is a perfect cube. And if we had to determine, okay, what's the cube root of that number without using a calculator? Each group represents one number that's in there. So one group of 3s would represent 1 3. Second group of 3s represents another 3. Group of 11s represents 1 11. So 3 times 3 times 11 would give us 99. And you can double check that with your calculator. So you can type in the cube root of 970,299 equals, and you should get 99. Okay, that takes us up perfectly to 330. So before I let you go, is there any questions on that at all? There's my dog again. Sorry if you could hear that. Okay, if someone's typing something, I'm just going to take it out here. So I'm just going to jump up to D2L. I'll come back there in a second and read that, Jonathan. Just to remind you to find the questions that we recommend that you work on. Go to the content page in our site on D2L, and you want to find the weekly guides here. And just the week 1 will be up for you. Okay, and then we're going to find lesson 2. That's what we did today. Click on that. It's a checklist. It will tell you everything to go through. There's some videos if you want to watch. It will tell you exactly what to do step by step here. And it will tell you what assignment questions in each step as well you should work on after you get there. So there's some assignment questions to do here. And you go through each step, and there'll be some assignment questions at the end as well. So just make sure you read through each piece so that you're not missing. It's not just the last part that has the assignment questions. It breaks up into pieces for you. So make sure you read through each checklist item so you're not missing any assignment questions in there. So there's some at the end. There's some here. And I think that's probably it for this one because it starts at question 1 here up to question 7. And then question 8, 9, and 10. So just certain parts of it. So don't feel like you have to do every single question. Try the ones we've listed here, and if you're really getting it, obviously don't keep pounding away at it as long as you feel confident that you've got the concept down. Okay, let me just jump back here. Yeah, so the Friday quiz, Jonathan, will open up at 8 a.m. on Friday morning, and I'll remind you guys about that tomorrow because tomorrow's Thursday. So I'll just remind you in the class tomorrow that your assignment or that quiz will open up at 8 a.m. and it will be available all day. So the last time you can access it will be 11:59 p.m. But once you start the quiz, finish it all right in one chunk there. You get 90 minutes to finish it. So you get an hour and a half to get those 8 questions done. Most of you won't take even close to that time because it's a fairly quick one. But once you open it, you can't just leave it open and come back to it all day. Once it's open, it times you. So make sure you have about an hour and a half time when you sit down to open it to start the quiz. Yes, you too. Okay, any other questions, anyone? If not, you can head out. I'm going to just shut the recording down. Again, thanks for coming, and I will see you tomorrow at 2.